Okay. Okay, so you got a capacitor, has a constant electric field. We don't have to use calculus for this, so this is why we like it. So work is equal to force times distance. You could say the work done by electric force. You could also say it's the synonymous to say the work done by electric field is force times distance. We're going to look at the component of distance that's parallel to the force. So electric field is the promise of electric force. That force is realized or fulfilled when you take the electric field, multiply by the charge that's in there. So this is an expression for the force, so we can substitute in here. So you have this expression. And in this scenario, go ahead and look at this question, pause the video. Correct answer is it's doing negative work. As it goes from right to left, it's not wanting to do that. The electric force is going that way, going in the opposite direction of the force. So here, the work done by conservative force equals a negative change in potential. Switching this to a proton, go ahead and pause the video. Correct answer here is positive work, and we're decreasing potential energy. Okay, so electric potential difference is the promise of the change in electric potential energy. We just talked about that, and so I'm going to substitute this in for that because of this thing. So the work done by the field is equal to the negative change potential energy. This is the promise of a change that's realized when we take a charge. So the correct answer is... Oh dear. Okay, we're going from left to right. Oh dear. Look at those italicized things. Okay. The work going from left to right. We are gaining electric potential. We're climbing in elevation. Okay. The force is going this way. We're moving it this way. Okay. So we're making it do what it doesn't want to do. The work done by the field is going in the opposite direction of motion, so it's a negative 40 volts per charge. Good with that? Okay. Now, here's the culminating. Here's what we're going for. So we have this expression for force affects energy. We've come up with this idea of work that quantifies, that helps us calculate how much, like what force, how much a force affects the energy. Well, we have this expression for the promise of a change in energy. We have this expression for the promise of a force. Wouldn't it make sense that there's an expression that ties these two together? Here we have force affects the energy, the promise of the force, and the promise of a change in potential energy. Okay, so we're using these promises, and we're substituting in for what we have here, and the realization of these promises, we don't need the charge. This is just based on the promises. Does that make sense? This right here is really crazy important. This right here is the algebraic expression. It'll become calculus here in a week or two. Okay, but the negative change in electric potential difference is equal to the electric field times the distance. Okay, this is, okay, when I was in your shoes, that was hard for me to digest. this was easier for me to digest. I could wrap my mind around this easier. Force times distance, that's equal work, and work is equal to the negative change of potential energy. Okay? And I would tie it to gravity. Okay? But then this is just saying, okay, the promise of potential energy, change of potential energy, this is the promise of the force. Okay? This is a really important equation, which we are going to take some time to digest. Okay? So, we're going to move on strength of electric field. The distance between the two charged plates is 1 centimeter. All right, so we've got a difference of 70 volts. Okay, is equal to electric field times the distance of 1 centimeter. So I've got, I'm going to change that to meters. So I get 7,000 volts per meter is the unit. But I thought electric field was newtons per coulomb. Volts per meter. Well, it's in an equation. It's got to reconcile. How do we... Okay, so volt is a what? Joule per coulomb. And a joule is a what? Kilograms meters squared over seconds squared. Like 1/2 mass times speed squared. Okay. Over meters. Okay, that knocks out. Hey, what's a kilogram meter per second squared? That's oh, sorry. Sorry, forgot something important. Per coulomb over meters. There. That's a newton per coulomb. Look at that. Okay. I had a buddy in college. I would not recommend this. He skipped all of his E&M lectures. The day of the test, he would look at the equation sheet. He would memorize all the unit conversions. He just did unit analysis, and he passed his class. He was a smart kid, but like the power of unit analysis is usually an unrealized tool. You right with that? Did you see her giving me a finger? I do see that. Huh? Good? All right. So, a way we can interpret this conceptually is this negative sign as we are moving in the direction, if we like along this landscape, if we're moving along in the direction of the electric field, you will always be going downhill on the landscape of electric potential. That's what this negative sign is telling us. Okay. If you're progressing, if you're traveling, you're sojourning across this landscape, if you're going in the direction of the electric field, you're going to a lower electric potential. Okay? Why? Because electric fields go out of positive into negative. They're going from mountaintops to the sinkholes. Everybody out with that? Okay. The second thing is this ratio is kind of looking at the slope of the steepness of the landscape. What do I mean by that? Here, if you're looking at a topographical map, I hope I put this. Doggone, why don't I not ever put that? Come on. There. Sorry, I'm going to deal with this right now. Okay. So here, if we're hiking through this, if you started at point A and you needed to get to that mountaintop, there's a hard route and an easy route to go. The hard route would be to just gut it. Okay? This is a really steep ascent. Does that make sense? You are changing your elevation quickly. Your rise over your run, you're rising a whole lot for a little bit of a run. The easy way would be to like circumnavigate and kind of go up that route. Does that make sense? Okay. So steep, that's like kind of flat. The steeper the slope, the stronger the electric field is. That's what I want you to learn from that. The steeper the slope, the faster this is changing. You rise over your run, the higher the electric field. Okay, and that negative just means you're going downhill. Good with that? I want you to be able to visualize that landscape. Okay. So here, this would be a saddle point. I recognize that my diagram isn't, it should be like upside down, but that saddle point here is this point here. Has a weaker electric field. It's shallow. Okay. All right. So that's my lecture. Here we go. Let's put it to work. Oh, sorry. If I ever do puns, I am 100% unintentional. My brain doesn't work in puns. Have a conversation.
Yeah, but then the positive and the negative forces. If the external force is negative, then yeah, which is no positive just means it's not putting this on. It's not the absolute value of the external work. Yeah, the external. Why would you? My hands are external force doing positive work. Actually, we're sitting on the side, right? Gravity is the aerobatic circle. Yeah, I was thinking. The work of Joe Biden, you right? Exactly. Yes. See for yourself. See what it's very good because it's the green though.
Correct answer is what do you say?
Where you get
A is true. Okay. If I didn't specify, oh, you can't see that. I didn't specify if moving at a constant speed or start to stop at rest. This would not necessarily be true because of the external, because of that thing. Everybody okay with that? Like I had to specify this for this to be in that equation. Okay. Tell your neighbor.
Okay, so this is okay. So this is what I was talking about. So I was just confused. Okay, so my statement basically I was confused. All is C.
Correct answer is C. Okay. This is like you trying to walk a big dog that's chasing after a squirrel. Like you're the external agent. The dog's trying to get to the squirrel. Like, no, 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 no. You're losing, but you're able to hold him so he's not accelerating and moving at a constant speed. Is everybody okay with that? Okay. So the constant speed tells us the net force is 0. Thumbs up when you have a guess. Tell your neighbor what you think.
C, right?
Correct answer is C. Are we good with that? Crazy cats. Same question, different scenario. Everybody good with B? Is everybody good with that? Okay. Real fast. Let's see. Just no B. Beautiful butterflies. Okay, so unrelated to this question, this equation here for electric potential energy, whatever, dr, whatever, not r, not squared. Okay, this is so the potential energy is equal to 0 when d is equal to infinity. Like just like gravitational potential energy. So when we're talking about on the free response, they were talking about work being done. We take that from starting at a place of infinitely far away and bringing it in. That's how you kind of like conceptualize where this expression comes from. Okay, because what they're going to do is say, okay, so the work is equal to the negative change in potential energy. The change is equal to final minus initial. We're going to make our initial location infinitely far away. So we're going to make our initial position 0. Okay, good with that? I'm just trying to give you context to think about this conceptually. Okay, when we're here in a plate, there's an electric field already established. This is like if you have a point charge and then you bring in another point charge, bringing that in from infinity, how much work is required to do that? That's your expression. You okay with that? Nope. Not good with that. When using this equation, just like gravitational potential energy, consider this as your starting point. You want to start or a place where it's ground zero, where your gravitation or your electric potential energy is equal to 0. Okay with that? Okay. That will help you on the homework. Good question. Like this, that is very, very AP-esque. That's AP-esque. They don't. They wouldn't. But they will say this and this, this and this, this and this. Like they take two factors and they go, is it like this? Is it like this? Is it like this? Or is it like that? Or whatever the. Have a conversation.
Because positive charges the charge will still move in something like type. So the area thing, the electric field is constant in there, and the charge that moves.
Okay, what do you say? Correct answer is D, dangerous dinosaurs. Okay. Positive things will always go to a lower electric potential. And where the electric field, no, forget that. Goes to lower electric potential. But negative things go to a higher electric potential. They climb uphill. Positive things go downhill. But they will always, both cases, regardless of scenario, naturally want to go to a place of a lower electric potential. So, like, think of it this way: if you have a hill and a ball, naturally it's going to go to a place of lower gravitational potential energy. Okay. It's helpful to compare gravity and electric field. Okay. And potential energies. Okay. We started at rest and we ended at rest. Thumbs up when you have a guess. Have a conversation.
Oh, okay, yeah. I didn't see the forget the sand in the bill. It's like, where is he has
Okay, so everybody go with D, path independent. Okay, does not matter. So long as you start and stop at rest, your net work is equal to 0. So the work done by the field does not matter. Path independent. Therefore, your external work, your external agent doing work is also path independent. This one would be doing what would we do? Positive. So this would be doing, you'd be doing negative work, no work, positive work. But overall, it's just going to be the same as just going from here to here. Okay? Work is a process, not an instant. Thumbs up when you have an answer. Everybody okay with E? They have the same amount of charge in a constant electric field. They're going to experience the same force, just in opposite directions. Good? Okay. Same scenario. Which one has a larger acceleration? Think. Think. Tell your neighbor. Tell them why. Yes. Correct answer is B, electron, because it has less mass. Okay. Good question. Same scenario. Think, do not influence or be influenced yet. Thumbs up when you have a guess. Converse. Tell them why. Correct answer is C. They both experience the same force for the same distance. That's the only thing doing work. So that's equal to the net work, which is equal to the same change in kinetic energy. Good with that? They both started from rest. Have a conversation. Consider this Scenario, a ball and gravity. I throw it straight down, I throw it out horizontally. They're going to hit the same speed. Not the same time, but with the same speed. Mechanical energy is conserved. Good with that?
So their speed in the x direction is, well, the y direction is the same.
No. Y direction is different because we're shooting this in the Y. This is going to the X.
Oh, I did not read that at all.
Okay, good with that? Okay. I'm just going to throw this out at you. It's going to seem overwhelming. I'll post this. But this is the summary. This is the summary of all, like how these measurements are all related. Okay. So like these are vectors. I'll post this on Canvas. These are scalars. This is the actual stuff, the force and the energy. This is the promise of the stuff, force and energy. Okay. I'll post this on Canvas and the equation sheet. We got free response questions due on Tuesday.